everyone, and welcome to this webinar on Operational Modal Analysis with ARTeMIS Modal. It's great to see so many of you have signed up, and I'm also thrilled to recognize some familiar names from our last webinar on Experimental Modal Analysis. So thank you so much for the interest. Today we will dive into ARTeMIS Modal Pro and explore its key methods and features. And as always, you are very welcome to ask questions in the chat throughout the session, and then Palle will address them at the end. If you have any questions regarding licenses, including the different ARTeMIS versions or pricing information, feel free to ask and I will answer them as we go along. You can also reach out to us at any times at sales@swips.com if you're interested in getting a free trial afterwards. And with that said, I will hand it over to Palle Andersen, so enjoy the session.
Thank you very much. Yeah, I'd like to welcome also, I just need to share my presentation here. Hang on. Guess it's running now. So I hope you can hear and see the presentation. My name is Palle Andersen and I'm going to talk about Operational Modal Analysis this afternoon here. It's 3 o'clock here in Denmark. So let's get started. For the next, I think, an hour or so, I will try to give you an introduction to Operational Modal Analysis first of all. Then dive a little bit into a tool that we are using very extensively in the software that allows us to see what's actually what we have of data and quality of it and so on. We call this the Singular Value Decomposition. And then I like to talk about two ways or two different types of operational modal analysis. One where we have a long record of persistently excited the structure, you know, and the other one where we have a single transient input, some short impact affecting the structure, and then from there we will have to extract whatever we can get out of it. So we will try to see, you know, how the different ways to operate the software depending on this type of data that we load in. And then we have some final remarks in the end. So this is the idea. Just to dive into operational modal analysis, let's start a little bit light. Just introducing a very simple structure that is vibrating. This is, you could say, in physical domain. So if we in some way could amplify the vibrations that this structure is having, then it may look something like this for this particular structure here, that it has been excited and it's now vibrating in a way in physical domain. It's a mix of many modes, all the different modes that has been excited at the time where excitation is supplied, that makes the structure then vibrate in this pattern here that we see here. So what we do in modal analysis, that is, we try to go in behind the scene and then extract the different modes of vibration that is summed together, causing the vibration that we can observe. And the most visible part of a mode is the mode shape, and that's what we try to visualize here. So there is a mode shape of the first mode of vibration looking something like this. And then there is another one, this is the second mode of vibration that has this mode shape here. But besides the mode shape, a dynamic mode is also described in terms of natural frequency and the damping ratio. So there are these two additional parameters that describes a mode. Modal analysis is, you say, something that has been around for many years, probably 50 years or more. But in the old days, it was an analysis form where you actually had to also measure the input and the output in order to be able to extract the modal parameters. When you have this type of analysis, this is in our term called experimental modal analysis. It's also called classical modal analysis and other things. But no matter what, it's the same that we would like actually to get out. We would like to know the modes of vibration, or the modal parameters as we call them. Then there is another technique that you can use in order to observe what's going on in the structure. That is when you want to just look at what's going on over here in the physical domain. And there you can observe both in frequency but also in time domain what is actually causing vibration or how the vibrations are looking. This can be done by something called operating deflection shapes analysis. So there are these three types of analysis that in many ways, have been used together or as complementary tools throughout history. In the old days, where operational modal analysis was not around, the best one could do when you only were able to measure the response of a structure, that was to do operating deflection shapes analysis, and then hope that the different modes of vibration, they were what we call well separated, because then the mode shapes that you could see in operating deflection shapes analysis is more or less the mode shapes of the structure. But today we have all these different complementary tools. We still are using operating deflection shapes when we want to see the mix of the different modes, how this is actually causing the structure to vibrate. If we have the ability to take our structure into a lab and isolate it from the rest of the world and excite it with some measurable forces, then we can do experimental modal analysis or classical modal analysis. If we are not having this luxury that we can bring it into a lab, then we have to just accept that it's out there in Mother Nature somewhere and being excited with something that we cannot really control. We can put sensors on it, accelerometers for example, and then we can measure the response, and we can use then operational modal analysis to extract the modes in what we could say is the running conditions of this structure here. So these are the different tools that is available when it comes to vibration analysis of a structure. Experimental modal analysis, as I said before, requires that the structure can be excited by some kind of excitation that we can measure. And there are different ways you can do this, but one normal way of doing it is to use a so-called impact hammer that is looking something like this, where we then have a force transducer sitting out here. So when you impact the structure, you can then measure the force that you are supplying. And at the same time, you can then measure the response of the structure with accelerometers, for example. And having the output and the input measured allows you then to extract the modes of the structural system that you are testing. The only requirement we have for this type of analysis is that this structure behaves linearly. So it means no matter how hard I impact this structure here, in theory it should not really matter. The modes that comes out should be the same. In reality it's probably not like that, but this is one of the requirements that we have to put on it. Another thing we have to assume is that the structure is not changing its parameters during our test. So while we are measuring on it, we cannot have that the modes are changing frequency or damping or something. It has to be constant parameters, because when we extract them, this is the assumption that we are doing. We are assuming that it's the same all throughout the measurement. So these are the two essential assumptions for doing a modal analysis of a structure. This is experimental modal analysis, and we then have to do a little bit of extension to the framework, you could say, when we switch to operational modal analysis. Here we have to do something, because normally we can only measure the response. We are not able to measure the actual excitation forces that are acting on the structure. And this, of course, causes problems. It means that we have to start assuming things. And what we do is we assume that these excitation forces here, they are basically originating from something we call a Gaussian white noise. That is an input that is completely flat. It has the same energy at all frequencies, and it's exciting all the frequencies in the measurement range we are looking at. So this is the assumption, and In order to make it work, we normally insert this kind of shaping filter that allows us to shape the excitation so that it matches what we actually have in the Mother Nature. But what is essential is that it's a broad-banded excitation that is stationary, exciting the structure in multiple points throughout the measurements that we are doing. This is the normal assumptions that we have to do. Otherwise, it's the same. It's the linear and time invariant structure that we have to assume. And based on this, we can then extract the modes of vibration of this structure here using the operational modal analysis tools we have available. So this is essentially the framework that we have to switch to, where we have unknown excitation forces. So you can say the mathematical assumption that we are using is that we assume that we have Gaussian white noise excitation. We assume we have a linear filter, a linear structure. And that means when we now excite this structure here with Gaussian white noise, what comes out at the other end is Gaussian distributed data, the response. And that means that we can actually fully describe it with the mean value and the correlation functions of this data here. These two moments, you could say, fully describe the behavior of the structure then. And this is the normal mathematical assumptions that we are putting on this type of analysis here and the structure. In practice, it means that we have to assume that we have some excitation that is broad-banded. That means it actually excites the frequency range where the modes are that we are interested in. If there's no excitation, there will be no modal response, and you will not be able to find these modes. It's really important that you have some excitation that excites the modes that you're looking for. And then it's also a very important assumption normally in operational modal analysis that we have multiple random and independent inputs that persistently are exciting the structure. So all the time input is being bombarding the structure with so that it can actually vibrate in different ways. The best way of actually simulating this is simply to take a small pen and then tap on a structure if it's small, because then you get these multiple inputs that are random and constantly exciting the structure in different ways. So this is a really nice way to excite a structure. There is different ways you can try to describe how long do we have to measure. But one of the rule of thumbs that we use is that if you have the lowest mode of vibration, the most low frequency mode, if you take the cycle of that one, that means 1 over the frequency, and then you multiply it with a large number like 1000 or 2000, this is a really good guideline for how long should you measure in seconds in order to actually capture this mode here. The high frequency modes are no problems because you have much more cycles available. At the same time, it's always the low frequency mode that is a problem because you have the fewest number of cycles in a fixed amount of data. So this is a kind of a rule of thumb that we're using, and this is good when you have a structure that is persistently excited. Now the problem is, what happens if we have a structure that only is excited by a single impact? Say it's a bridge, there is a boat coming and it's just suddenly colliding with the pier of this structure here, and the structures now vibrate and dies, the vibration dies out. So we have a single short time input causing vibrations of this structure here. How can we then analyze this? Because this is actually a little bit far away from all the different assumptions that I've just put up here. So this is some of the things that I like to describe a little bit later in this webinar here. What can we actually extract from this type of data, and how can we extract it? Because it's a little bit different from what we normally do in operational modal analysis. So this is something we could call a transient response analysis that we do there. So let's come back to that a little bit later. What I would like to do now is just to introduce another tool, or the essential tool, I would say, that we use in ARTeMIS, and that's the Singular Value Decomposition of frequency domain data. And it all starts with a matrix. When we are measuring, let's say, 3 channels on the structure, we can then take these 3 channels of time data, we can chop it into different segments, and every time there is a segment of data, we can now perform a fast Fourier transformation of this, and then we can multiply this with a window, or the data with a window, and then make the fast Fourier transformation, and then sum it with all the other data segments that we can chop up this data series up in. When we do that, then we will get a spectrum. There will be autospecters, so there will be one autospectrum for the first channel, for the second channel, and the third here, and we will have some cross spectral densities also. This is a matrix that we can then construct for each of the discrete frequencies that we obtain from this fast Fourier transformation. So you should imagine that we may have 1024 of these between 0 and the Nyquist frequency. But each of these, at these frequencies, there will be this kind of matrix here of spectral densities. So that means when we have 3 channels, we basically have to look at 9 different values at a frequency to actually find out what's going on at this frequency here. So you can imagine if you have 100 channels instead, then it's 100 times 100 spectral density values that you will have to look at in order to be able to determine what's going on at a certain frequency. So things are really increasing a lot because it's a power of 2 that things are increasing in compared to the number of channels. So for that sake, it would be nice if we can make some kind of diagram where we come back to the original number, the number of channels. And doing a singular value decomposition, which is defined like this, where we have our matrix we want to decompose. Now we decompose into these 3 matrices here. This one here is the left singular vector matrix. There is a diagonal matrix here of singular values, and then there are some right singular vectors over here. When we do this, it's basically we rotate the original matrix so it becomes diagonal. And then the rotation we do is described by these 2 matrices out here. So these are the ones that allows us to come back again to the original matrix after this. It's basically an eigenvalue decomposition we're doing. You should imagine that you take this matrix over here and you multiply it with itself, where you have made a Hermitian transpose first, and then you take the eigenvalues of it. What you get out of that are the singular values. So when you do that, when you multiply something with itself, it always becomes real in the eigenvalues, and that's why we have now real valued matrix over here. The singular values are real, and they are ordered in a way so that this singular value is always larger than this one, that is always larger than this one, and so on. So this is the singular value decomposition. It diagonalizes a matrix, which allows us actually to study the content of this matrix here just by looking at these 3 numbers here at this particular frequency here. And this is really nice. So that means what you have seen before, you are having a matrix. We have a stipple line here. For each of the channels, there will be, this is the first autospectral density of the first channel, defined from 0 to the Nyquist frequency. Here we have the second or autospectral density, and then we have the third here. For each of these that are all defined between 0 and the Nyquist frequency, we can now take out a certain frequency. So the stipple line here is just some frequency we take out, and then we can stuff the values into this matrix here, and now we get this 3 by 3 matrix here of spectral densities for this particular frequency here. And what we get out in the other end after we have made the decomposition is that we now get 3 values. So we get the first singular value, this one here, that's the one you see here. The second is this one, that one, and the third is then the one you see down here. So you can imagine we do that for all the frequencies like this, and then we get this nice looking diagram here where we now have 3 lines for the 3 channels we have to look at. And you can get a lot of information out of this diagram here, and that's what I like to now present, what it is that you can actually get. We can start just making a structure. We take a structure that is rectangular. This is a rectangular plate I have analyzed here. So what you get out of that is you get modes that are vibrating this way here and then the other way also at different frequencies. When something is rectangular, we get it's a non-symmetric structure, and we get actually well-separated modes. The way we can see that in the singular value diagram is that we will only have the first singular value here basically having a peak, as you can see here. The second singular value comes up to this point here, but this is just to indicate at this particular point here we are leaving the domain where this mode here is having most to say, and now we are entering the domain where the next mode is the dominating. So the point you see here is simply where it exchanges. You can also look at the mode shape. The mode shape will at that point change from the first mode to the second mode in this way here when you try to find the mode shapes. So this is this is when you have a well-separated modes of a well-separated modes of a non-symmetric structure. Then it will look like this. In this case here, there are 2 modes that are a bit close to one another. We can amplify a little bit here, but you can still see that it's the first singular value that has peaks. There are just 2 very closely spaced peaks here. So this is 2 closely spaced modes we have here. And again, the red value that you have, the second singular value, is just pointing to the point between the 2 modes where the domination, you could say, is changing from one to the other. So this is 2 closely spaced modes that we can see like this. You still have 2 distinct peaks in your first singular value. The next could be a structure that is symmetric. I've made a test on this small item here. This has, you could say, 2 axes where you have symmetry. And that means that you will now have 2 modes that has the same, that they will be vibrating at the same frequency, but with 2 distinct mode shapes. So there is a mode shape this way, and there is another one this way, in this case here. But the frequency it vibrates at is the same. The way this looks is like this. Now you have 2 singular values pointing to exactly the same frequency. So there will not be 2 distinct peaks in the first blue one. No, they are now both pointing to the same frequency, the 2 singular values. When you see that, then you know that it's a symmetric structure that you are testing that has 2 modes that are vibrating at the same frequency. And when you have 2 modes, it means that you have 2 symmetry axes. If you are testing something with 3 symmetry axes, you would have 3 of these popping up here. If you have a cylindrical structure and you are able to excite many of the modes, you will see a lot of peaks pointing up to the same frequency. You will not see an infinite amount of modes because you cannot excite all of them, but there will be a huge amount of peaks coming up to the same frequency here because of the cylindrical nature of the structure that you are testing. So this is when you have symmetric structures, then you will get what we call repeated modes. This is another nice thing you can see from the SVD. You can also look at the quality of your data. If you for some reason forgot to excite the structure after you plugged in your sensors and you started doing your data acquisition, you will most likely be able to see something like this, where there will be a whole range of singular value lines here that are completely flat. And the first flat, you could say, that you have down here basically indicates where your noise floor is. So everything above that you may be able to find, everything below that, forget about it. So this is the indication that you get when you get a flat singular value. And you can basically also try to make a judgment how much dynamic range do you actually have. It should be a quite high number, like 50, 60 or 70. Then it will be nice to work with the data. But you can actually look at it and do some kind of a difference between the largest peak here and then where you have your noise floor. That difference gives you a nice indication how many dBs you have available. And in a case like this, it's probably, I don't know, 40, 50, 40 perhaps or something that you have. This structure here, I forgot to tap on it. This was still the same steel plate from before, but when I then started tapping on it, the exact same structure starts looking like this when we look at the SVD. Suddenly you get energy pumped into all your modes, and they all pops up, and you can very easily now see all the different modes way ahead above any noise floor. The noise floor is probably at least from here or below somewhere. So there is really a lot of dynamic range suddenly, simply because we are now putting much more energy into the structure here. And this is of course what we are aiming for. You should see something that looks like this one over here when you do the test. If you for some reason don't have this and you cannot make more excitation or higher excitation levels, then you have to do something about the settings of your data acquisition. Okay, so finally we can try to look at when we have different number of inputs in the structure. And what we can see is when we have a single input affecting the structure, we will only have a single we will have a singular value that it has a high level compared to the others. If we have two inputs affecting the structure, we will be able to see two of these singular values here popping up at the same frequency, at the same time. Once we have multiple inputs, all the different singular values, they are popping up here, as you can see. So you can just by counting the number of singular values you have, you can actually determine how many inputs you have available during the test. And this is some of the things we would like to try to see when we are doing now the actual analysis of these two tests I made. I made one for the same structure with persistent excitation, and another one where we just did a single impact. Then just show the structure is this, it's called a JimBeam structure. I think we have a picture of it here. As you can see, it was hanging like this in some rubber here, rubber bungees here. And then we were placing sensors, 4 sensors here on this part here, and the same on the other side over here. So in total we have 8 channels available. I did 2 tests, one where we were just doing a random excitation with a pencil like this, so we were just tapping on this structure here during the test. And then another one where we simply used our impact hammer and just made a single impact somewhere on this structure here to produce a single transient signal of this particular structure here. So we have these 2 different tests available here, and let's try and see how it looks here. The first one, there are multiple inputs. I'm tapping around different places on the structure here, and this is typically if you have a structure that is excited by ambient excitation, wind or traffic or something else like that, then you will have multiple inputs that are random and also uncorrelated, so they will actually nicely be exciting the structure. And what you will see is that you will get nice singular value diagrams like this down here, where you can see you have multiple inputs like we described before, because all your singular values, they are popping up at the same time. So it's very clear to see all the modes in this case here, and of course it's also very, very easy to work with the data of this type here. So we can try now to just have a little look about how this looks when we load this type of data into ARTeMIS. I can start up ARTeMIS here, and then let's see if I can get it. So I will start by loading a so-called configuration file. I do that from this OMA option here, and then I have to go to the right place. Let me just see if I can open it so we can see it. So you can see here, this type of file here is a text file. It allows you to define a project, all the different things that are needed in order to be able to initialize a project. First of all, you have to put some kind of title. Then you have to put the sampling interval in seconds, that's here. You have also to put information about the geometry. So there are some node numbers here defined and X, Y, Z coordinates like this. Then you can put some lines between the different nodes you have defined up here. So you get some wireframe defined. And you can also make it solid looking by adding some triangular surfaces that allow you to get some triangles drawn between these nodes here. And then finally you can also link the measurements that you have made together with this geometry that you have defined. And you do that in this section here where we have a keyword called setups here. Here you tell what file that you're using, where are the measurements located. You also specify what type of file it is, and we support 20 different file formats or so. And then you have to specify, for each of the channels of the file, you have to specify what node it's located in this channel. This is channel number 1. It's located in node number 8. And it's also located in a direction called 100. That means it's plus X this direction here. And then there are some additional information here that is used to identify what type of measurement it is. Its unit is G and its acceleration, and there is also, of course, a label of the channel like this. So you have to do this for each of the 8 channels that we have available in this file here. You cannot leave any of the channels out. If there is a channel in this file you don't need, then you just put a 0 on this line here in order to bypass it. But you have to make sure that the number of definitions you have here matches the number of channels you have in the file. And that's it. Once we have this, we can now load this data here into ARTeMIS. And then we're actually ready to do an analysis. We can just, we have seen this probably so many times, so it's not something I want to go into details with, but just to see what's going on here. We have now actually processed the raw data. We have determined the spectral densities. And from there we have now, as you can see here, also the singular value decomposition. And then some other processing is going on behind the scene here, where we are now also estimating some modes for one of the methods that we are using. This is the one we call SSI-UPCX. This one here is, as you can see here, creating a stabilization diagram. It works in time domain. And for each of these models here that we have, that is from 1 to 100, in model order, determined. And for each of these we are extracting the modes. And we are now here in this diagram here presenting the frequencies of these modes. And we can see the ones that are red and lying on top of each other here on a vertical line. These are the stable modes of the structure that has been determined. And they are now automatically picked out. There's a small A up here indicating that everything here has been taken out and averaged together to form a global mode over here where we have an average frequency value here. We have also a damping ratio, as you can see here, that is an average. And the mode shape up here is also an average of all these different mode shapes that we will have for each of these modes here. So this is how the time domain methods, they are working on this persistently excited structure here, where we have 1.5 million samples. It works really, really good because all the assumptions are fulfilled, because we have all this data and we have all these independent inputs acting at the same time. This is how things should be. In reality, it may not be the case, but this is when it's like this, all the assumptions that the methods has been developed on are fulfilled. And this is, of course, very nice. This is one of the methods. Another one is one here that is working in frequency domain. So it's actually working on the singular values. And the way it works is that we simply are picking out the peaks here. So I just double click on each of these peaks here. And now I can now get the modes out here, as you can see here. And again, I get a frequency, I get damping, and I also get a mode shape, of course, every time. So this is one of 3 different frequency domain decomposition methods that you can use for this type of data here. So this is the normal use of ARTeMIS when you have, you say, the normal data that we like to have, where we have long records, where we have multiple input affecting the structure at the same time. You saw it in the singular values. You could see all the singular values are popping up, and that's the thing we like to see, because that means we have multiple inputs available. Let's try to go back to the slides now and then see what's going on when we have a single impact. Let's say that we have the same structure here, this structure here, and now the only thing that we will have available is that I impact a single time, then we do the measurement after some seconds, and then we get a time series that looks like you can see here. Where's my mouse? There. So here you can then see that you start a little bit after 0, but then you get a large impact, and then it slowly dies out here, as we can see here. This impact here can be short or long, but there is only a single one in a single location. And when we do, we take this into ARTeMIS and estimate the spectral densities. Then we get the singular value diagram, and you can see here now it looks like this. This is the same structure as we saw before, but here you can clearly see that there is only a single input, single location, and that is affecting this structure here, or that is exciting it. All the rest of the singular values, they are lying way down below the first one. So immediately you can see when you load this data and you get this type of diagram here, you can see you have a single input, and that's it. Another thing you can probably see is that before we actually had modes appearing here, peaks, they are really not there anymore. So from the position where we have done this single impact, we are not really able to excite the high frequency modes with this data here. So that means that we are now going to having single inputs, which means we cannot really, let's go back here and see, we have a single input like up here. Remember that in this case here, we actually had two closely spaced modes at this location here. When you have a single input now, then you have only a single singular value popping up here now. So you cannot actually now see that there are two modes anymore, because there is only a single singular value. There is not the second or third or so on that helps you. You only have one, so it can be very difficult actually now to see and separate closely spaced modes. And of course, if it's repeated modes of a symmetric structure, is even worse. Then it can be really difficult to separate these two modes from one another when you only have a single input available. So this is some of the things that we lose. We lose the ability to see everything we have of modes in the structure here because of the lack of, you could say, excitation of different points on the structure and so on. This is critical, you could say, but still there will be things that you can get out from this type of data here. Let's see. In order to make it work in ARTeMIS, let's try to go to ARTeMIS now. We will close this project here. And we will try to load some other data now of the same structure, this where we have this now single impact. So let's just go here. So it's the same configuration file, but now with other data inside. Let's go and see the data. Here you can see how it looks. So we have been impacting at a single location, and all the 8 sensors, they are responding with a free decay or single decaying function here, as we can see here. So this is what we have of data available. One thing we have to do now, I think it's also written here in our slide here, we have to tell ARTeMIS now that we accept that this data is not perfect. We have to allow ARTeMIS to work on smaller amount of data, because normally an impact and this transient signal is short, and normally ARTeMIS do not allow to work with less than 2048 samples. But here we allow that you can actually work down to 128 samples instead. So we have to tell ARTeMIS before we start doing the analysis that we actually are working on this kind of single impulse input. So you can see there is an option here that we have to shift. Inside ARTeMIS it's located here. I go here to the top point here, and now I can now switch here to this instead. It doesn't really make any difference in this task here, but it's just we need to do it before we go to the analysis task. That's why we do it here. And when we do that and go here to prepare data to start setting up the analysis, there will be some other things that you haven't seen in the previous settings. There will be a window available, an exponential window now that you can actually apply. There will also be the ability to actually extend and zero pad your data or your data segment that you are going to use for the spectral density estimation, so that you can get a higher resolution if you have a really short signal. So you can do that by clicking this button here, then you will get more in. We will actually only have 2048 if we did not check that one, but now we get other options here that will then zero pad the data so that it becomes longer, you would say, in the end. And then when you do the FFT, you can then get a higher resolution of your spectrum. So this is something you can do in this case here now. What I recommend for this type of analysis, when you know you have a single impact that is just dying out, I would recommend that you take one segment and make one long FFT and a single one to produce your spectrum of this one here. So I will just go to the maximum available resolution and choose this one here, so that I can see that the number of averages I get is 1, which means I only have a single segment available. This is at least something that I can see. It means that you use the full signal, you're not chopping it into 2 or 3, and that seems to actually improve results a little bit. But this is what you have to do in order to start working with these very short signals, especially if you have a single transient signal. What I also write here is that we have this exponential window available. I'll come back to that. And in some way, I also recommend that you perhaps stay in the frequency domain, because our SSI tools have been developed under the assumption that we basically have infinite amount of data. And this is certainly not the case when you have this short impact, and it can affect what you get out of the SSI tools. So at least on my own personal level, I will use the frequency domain methods in order to extract the modes. So what we will do is we will also, in many cases, have to apply a so-called exponential window that is defined like this. There is a kind of a factor here, beta, that is a number that allows this window here to go from a large value and then die out. The way this value here is determined is that we select what would we like to decay to in the end here compared to the initial value. So if you set it to, let's say, 5%, it means that the level of the window here is only 5% of the initial level that you have up here. So when you multiply this window here with your data that you have recorded, then you end up with a signal over here that dies out to 0 here. And it's very important that it starts at 0 and it dies out at 0, because we need to have this periodicity defined in order to use the FFT in the right manner. So this is very important. So that's why we have to multiply with the window if we can see that our signal is not dying out in the end here. One thing that is very important is that when we apply this type of window to the data, we are actually adding additional damping. But it's a damping that we know, because it's defined through the beta value here. And that means we can also compensate for it. So when we have estimated the eigenvalues of the different modes, we will then add this beta to the real part of the continuous time eigenvalue before we extract the damping and the frequency. In this way, we then get a damping that is corrected, compensated for the added damping that we are supplying. So this is just something, and this is done internally in the software, so it's not something we need to pay too much attention to. Let's go to the software and see how it works. I will now try to add perhaps decay down to, we could also try 1% like this. So that means that we now, on top of the data, we multiply this window here that makes it die out, so that it will only be 1% the window in the end here compared to the initial value. If we do that, we can also enable a little bit of SSI just for fun, and then see what we get. Now you can see the singular value decomposition here, very much different from the one we saw before. And this is of course because of the single impact. There is a single input acting on this structure here, and this creates all these obstacles for us now. But we can still go to estimation. Now I want to go to the EFDD again, and here we can now do an estimation of like we did before. And what we will see, I can just do a little bit more like this. Oops. As you can see here, So we can get these modes here. We cannot get the higher order modes, but we can get these well separated modes here up to this point here. What you can see written down here is now that the damping has been corrected due to the exponential window. So we get this little information here that because of the added damping, the damping of these modes here that you see over here are actually corrected so that they are not being reported too high that they would otherwise be. So this is one of the things that we have to pay attention to. But you can see, you can get data out of your, or modes out of your data, even though you only have, you could say, a limited amount of input available. But of course, in this case here, this is a well-separated structure. If it was symmetric structure, if there was some higher order modes you wanted to find, it could be very problematic with this type of input. But you can actually get information out even of these limited signals that we see here. So this is what is you could say transient response analysis using ARTeMIS. So as a final remark, between all my coughing and lack of breath, I was able to, I think, present the Singular Value Decomposition and how we can use that one to assess the quality of the measurements that we are doing and what type of structure it is we actually are dealing with. Is it well-separated modes, or is it closed space modes, or symmetric structure with the repeated modes, or what is it? I also introduced how we can work with short time series data from single impacts, for example, how this can be handled by ARTeMIS, especially by our frequency domain methods. We recommend using the frequency domain methods because using the FFT with the exponential window actually allows you still to extract whatever is in the data. If you're using the SSI methods, you are violating the assumptions quite heavily, where we need infinite amount of data basically. So we are not really recommending that you use those. I think in this case here with this structure here, they work quite good, but with shorter, more noisy transient signals, you will get into troubles. And then finally, of course, the problem of using transient signals is that you may not get all the modes of the structure, because not all of them has been excited by the single impact location that you have available. But still, in some cases, it's just necessary to work with what you have. What we have done here is something we have developed for a project that we are working on, where we are looking at what happens if you have a ship vessel that is being impacted by, let's say, a missile. The only thing you will have available right after this happens will be a short transient signal. But it's still important that you can actually extract, hopefully, as much information that allows you then to assess, are we still okay or are we not okay with the structure? So for some cases, it's still important, even though you just have to accept you cannot actually get what you want, but you have to work with what you have instead. That's why we have developed this. All right, so thank you for watching in. I hope you got some out of it. There will be something lying on YouTube, I think. I hope I can filter out all my coughing. But you will be able to see here at our YouTube channel, you can see other videos also about operational modal analysis and experimental modal analysis and structural health monitoring. We have our next user training course here in Aalborg in Denmark in April. And if you are interested, there are still seats available, so you can just contact us and then we will send you the information about it. The next webinar will be in the autumn, and then we will talk about the experimental modal analysis we have in the software. So thank you very much for listening in today.